Alright, in this video I'm going to talk about the transition metals, and I'm going to talk about why they have some common chemical properties. With this in mind, we have to remember that we're using a slightly oversimplified model of the atom. This video is still going to talk about this from the perspective of the Bohr-Rutherford model of the atom. If we use the quantum atom or the Schrödinger atom, then this would all make a little bit more sense, and maybe I'll do a video like that later, but right now this video is intended for grade 11 chemistry, so we haven't quite gotten into that other model, the atom, yet. The trick here is that when we put electrons in orbitals, we sort of have to this point been assuming that we always fill from smallest shell to largest shell, and that we just always take the next available spot in the smallest shell. But it's a little bit more complicated than that. Those shells aren't all the exact same, and they sometimes fill in some complicated orders. And the reason then that the transition metals all have some common properties results from that. I think it'd be easiest if I just showed you with the Bohr-Rutherford diagram that you would get for zinc. So let's start with that. So zinc has an atomic number of 30. And an atomic mass of 65. That's a 30. There we go. So that means it has 30 protons. 65 minus 30, 35 neutrons. And we're going to have a lot of shells here, so bear with me. We're going up to 30 electrons, so 2 in the first. 8 in the next one. And then in the next one, we will go all the way to 8. If you're counting here, we're up to 18 on our way to 30. Now here's the trick. Before the shells that electrons go into, we might have told you that it was 2, 8, 8, 8. Like that. But this is a slight oversimplification. It actually follows the pattern 2, 8, 18. So that's 2 times 1 squared, 2 times 8, 32, and so on. So this shell right here can actually hold some more electrons if it wanted to. But due to these things not filling in the normal order, what actually happens in this situation is that this atom starts a whole new shell. So for the next 2 electrons, we put them way out in this shell. And what that means then is we don't finish this shell before we start the next one. Then for the next group of electrons, instead of putting more out in this biggest shell, we can actually start adding them back to the inside shell. So let's do that here. So we're at 2, 8, 10, 18, 20. So I have 10 more to put in. And there's my 10 more. And that gets me to 18 in that inner shell. 2, 4, 6, 8, 10, 12, 14, 16, 18. Yep. And so it's full. And there's no more that can go into that shell at all anymore, and now we would start filling on the outer shell again. So because I put these 2 in before I started filling, before I completely filled this, to keep that simpler for you when you're in grade 9 or 10, often we tell you that the pattern is 2, 8, 8, ignoring the ones that go in later, and that's why we usually just work within the first 20 elements. But now that we're, trying to understand these transition metals, I'm letting you know that it actually can go all the way up to 18 in that inner shell. It just does it in a funny order. It sticks those 2 out before it fills it the rest of the way up. Now let's look at this. So here we have 30 protons. And we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28 electrons, leaving us with an effective nuclear charge of +2. So effectively, what zinc looks like is a +2 in the middle and 2 electrons hanging out on the outside. Now let's do another transition metal and see how it's different. Let's go with the smallest one we can do to try and speed this along. Scandium. Scandium has an atomic number of 21 and an atomic mass of 45. So it has 21 protons and 45 minus 21, 24 neutrons. And again, we'll start it off neutral. So we put 2 in the first shell, 8 in the next shell, and then in the third shell, we'll have 8 more. That'll get us up to 18. And as discussed, this inner shell isn't completely full yet, but we have our funny thing where we're going to start a new shell instead and put 2 out there before going back in and filling the inner shell. And that gets us up to 20, so I've got 1 more to give. There's my 21st one right there. Okay? So when I got to 8, I went out to the next shell, and then I had to go back in. In grade 12, we'll learn the exact order of how we fill these things and why that works. But let's look at this from an effective nuclear charge point of view. Here, I have 21 protons, and in the inner, I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 19 electrons for an effective nuclear charge of +2. So from a chemical reactivity standpoint, this looks like a +2 with 2 electrons around it. Well, hey, that's the exact same thing that we got for zinc. In fact, for all the transition metals, as you move across, you are going to end up with a +2 or something pretty close to a +2, resulting in your effective nuclear charge and 2 electrons sitting around the outside of it. So from a chemical reactivity standpoint, they have the same attraction for electrons because they have the same effective nuclear charge, and they have the same number of electrons to give. Now, again, the filling of these electrons into this inner shell can be a little complicated. They might want to put 1 in there earlier, or they might want to take one of these and put it in, and if that happens, that's why we get something like copper, who can be +1 or +2, because what that would have meant is one of those very outer electrons was on the inside instead of being on the outside when it formed its ion. Or if both were on the outside, then it'd be a +2. And we have some complex things that can happen here. But because we're adding protons and inner electrons as we move across the transition metals, so when we go from scandium, for example, to zinc, all we're doing is adding electrons on the inner and adding protons, and they're going up at the same rate. What that means then is our effective nuclear charge, which was, say, 21 minus 19 for scandium, will just become, this is protons, this is electrons, for titanium, the next one over, will just become 22 and 20, which is +2 or +2. And then for the next one, which is vanadium, 23 minus 21. See, we're increasing the number of inner electrons and the number of protons at the same rate, and as a result, our effective nuclear charge is staying the same. What this means then is that our transition metals all behave like group 2 metals. This is an oversimplification. Sometimes adding those electrons in the middle can have different effects, making the atom more metallic, as in more willing to give up its electrons, or less metallic, as in holding its electrons a little better than you'd think it would. But in general, that is the overall reason why they all have fairly similar, fairly common chemical properties. And so why we think of them all as basically a group.